Sorry, I think somebody may have just joined. Yeah, one more person just came in. Hello. All right, so we have a few people. We'll get started now. We're going to record the session, so please be aware of that. And we'll make the recording available to everybody who's not available. So if I could just ask everybody to mute themselves. In fact, thank you. That's great. If you do have a question, though, at any time, please feel free to unmute yourself and ask a question. You can also raise your hand in the Teams meeting, and then I will get to you when I have a chance. Okay, so starting here, so thank you very much. We're excited to be supporting the ARMA 2023 student competition. TASC has been doing this for a few years now, so we're happy to be involved. What we're going to, just a bit of an outline. So you should have all gotten a problem set, and you should have also have received these slides. And another person's joined. You can use any appropriate software tool or other tool, spreadsheets, analytical models, other software that you have at your disposal. We are, however, making FLAC 2D version 9 available to you free of charge. The licenses will be web licenses, and they'll be valid until February 29th of next year, at which time you should have completed modeling and your presentations. But feel free to play with it while you have it. So I'm going to start with instructions for downloading the software and a quick overview of installing the web license. I don't know if anybody's had a chance to do that yet. Essentially, just a couple requirements. So you can run the models either using Windows 10 or 11. Ideally, you have the latest service packs installed. You can also run the software on Linux if you have a Linux system and prefer that. There are different installers for each operating system. So if you have a question about Linux, just let me know and I can point you in that direction. For now, I'm assuming everyone's going to use a Windows. Processor, a decent laptop. It's not a very large or complicated model in terms of memory requirements. So i7 computer, laptop, or a desktop should be fine. We can't run our software currently on any Apple, so no Macs, unfortunately. Obviously, a reasonable amount of hard drive and RAM. And we don't really need a port because this is going to be a web license. So it will require that whatever machine you're running the models on be connected to the internet. So to get your team license, so you should all have received an email from Jim Hazard, who's our software manager. So he set you all up with web licenses, one per team. And if you have any issues in terms of the license, please let Jim, his email's there, know, or myself. Make sure to check your email junk folder. You may have gotten it through there. In terms of setting up your account, the details are really all in the email. And there'll be a link to create an account. It'll take you to a specific web page, and it will have you create an account. And you just have to basically provide your name, email, and some other information, and then you can activate it. In order to download FLAC 2D, you can download that from our website. I've included a link here. But if you're on our website, here, you just have to go to software, FLAC 2D. And then over here on the right-hand side, we can see a Tasco Windows 9 update. And you just have to download this file. Click and download whatever the current version of that is. And that will actually install a number of our software packages, but of course it's the FLAC 2D one that you're interested in. And you'll have a license for this, so that license, it'll be fully functional. These other products will be on your computer as well, but they'll run as a demo mode without a license. So really what that means is there's just a restriction on some of how big you can make a model. So when you start FLAC 2D, you'll see a dialog will pop up, and then there will be a link here to show your license location where you can enter your license, or you can go to once you've started FLAC 2D, you can go to the Help menu, License, and specify license location. Either works. You'll just see this at the first time you start up the software. And then you'll get a dialog that looks like this. You just have to click Web License, put in your email address and the same password that that was provided on the website that you set up the license initially. Save and exit, and then you should be good to go. You just have to do that the very first time. If you have any questions, let me know. Somewhere in my slide deck here, I have a slide deck or some slides for resources. It includes my email. And sorry, let me back up. I haven't introduced myself. Apologies. My name is David Dugagne. I'm a senior engineer responsible for technical marketing based in Minneapolis with the Task Consulting Group. So I have my contact information on one of the resource slides. And if you have any questions with the problem set or something's not working, getting your license, installing your license, please don't hesitate to send me an email. Yeah, so here are the resources. A couple of things. FLAC 2D includes built-in documentation. And I'll show you quickly once we start up the code how that works. But basically, there are a couple different ways to essentially access the documentation when you're working with the template. We have online help, which is the same thing. It's a web page instead of files on your computer. There's a FLAC 2D quick start example. If you want to sort of see an overview of running from the beginning to the end of a model, I believe it's a slope model. We have a software forum where you can go on and ask questions of other users and of Taskans. We have a software academy, and it has a few different things: an overview of working with our user interface, getting started with FLAC 2D, and an introduction to FLAC 2D, which is actually our full 3-day course. It's all split up into sort of bite-sized pieces for you. But if there's anything that you're interested in terms of learning how to work with FLAC 2D, that's fully available to you. I see I don't have the coupon code here, but I believe it was in the slides that I sent you. That'll get you free access to this course. The other ones are already free. Let me know if this wasn't included in the email or in your presentation, and I'll follow up with those codes if you're interested. So for support, we do have a general FLAC 2D at atascacg.com support email, but really for the purposes of the competition, just shoot me an email. So I'm just going to do a quick overview, just a little bit of background in numerical modeling, some of the key elements of the model and the template that we're going to be working with. I'm not sure exactly what background everybody has in terms of modeling. If you've used something like some rock science software or FLAC 2D or some of the other packages out there. But we'll just take a really quick run through so you've got a sense of some of the terminology. So FLAC 2D as a 2D piece of software assumes plane strain conditions apply. And really what that just means is that if you were to take if it was a 3D model, which of course in the real world, everything's 3D, you could take a slice anywhere through that model and you would have the same situation. So we have the same material, we have the same sort of model geometry, in this case, a couple circular tunnels. So in this case, this is well suited for any 2D software. If we have a geometry that in itself might work with plane strain situations, but we have a more complicated geology. In that case, or in this case, we have different topographies. So we have varying stress being applied as we move along the tunnel and different materials. In that case, what we can do as a shortcut, rather than necessarily running a 3D model, we can do a series of 2D models, 2D slices, where we'll have varying height of material above the tunnels and also different materials. And if you get into a situation where you really can't put a plane across the model and get the same situation, so here we have intersecting tunnels, that would not work very well in a 2D model. We have uh, a model that's not symmetrical. So different things like that with the combination of the complicated material and stresses, really that's a 3D model situation. So the model that we're working with, or the problems that we're working with today, will work nicely for a 2D plane strain situation. It's a fairly simple geometry. It's one material. Some terminology. So essentially we have a mesh or a grid that defines the problem domain. And it's just really a space that's being broken up into smaller regions, either quadrilaterals in 2D, or you can also have tetrahedrals and different shapes. So really 3 and 4-sided objects in 2D. Each of these elements are referred to as zones, and a zone is defined by a series of grid points or nodes. Between each node, there's also a face or an edge. So when we're also looking at a model like this, we can define different materials. So we can have, for example, say this is one material here indicated by the blue color, and that is granite. And then above it, we've got in this slope a limestone material. We can also define different regions. For example, if this is a cavern that we're going to excavate, in flat 2D, we can define groups. And then we can even say that the rest of this material is not the cavern, and that's the slope. So there's a way to use Boolean logic to sort of specify different parts of the model. A few more definitions. We have this concept in Itasca software of small and large strain mode. And really all that means is that in small strain mode, these grid points or nodes stay put. Yeah, even though the displacements and velocities of these nodes are calculated and can be displayed, and you can see a contour, the slope itself or the model itself never deforms. However, in a large strain model, these points, say for example along the pit face, are free to actually physically move, and their location will be updated as displacements or velocities change. And in this case, we'll see when we look at the template that we will be running primarily as a large strain model. So we'll actually see the deformation uh, and physical movement of the face of the backfill in the stope, depending on the strength of the material. Interface. So in flat 2D, we can define an interface, which is just essentially a plane on which we can separate one set of zones from another set of zones. And we can actually have sliding of those zones along each other, or separation. They can move apart or they can close. And so that's a really useful way of representing, for example, faults or joints in the rock mass. Boundary conditions. Um, they're essentially values of field variables, so stress and displacements that we predefine at the boundary of the model. And really what we're trying to do here is define the interaction of the model space or the domain that we've meshed and the rest of the world, how that interacts with the rest of the world. Groups and slots, when we look at the template, we'll see we take advantage of that quite a bit. Essentially, a group is a collection of objects, say, zones. Each group may also have many slots, which I like to think of as layers. So uh, this way we can have an object belonging to more than one group, and each group can have up to 128 slots. And so if we go back to this image here, these zones can be associated with a group called granite, which is the material it's made out of. And that can be one slot, or it can be defined as a physical domain called cavern, because that's going to be an excavation stage or something's going to be happening there in particular. Likewise, these zones here can be defined as being a limestone material or belonging to the group of limestone, but we could also assign it to something that is other than the cavern or cavern not, and we can call it slope. The actual names are up to the individual user to define whatever makes sense. And then groups use a range logic, which can be a physical extent, so sort of between some X and Y coordinate or within a area or a volume or a property. So an ID range or any zone or grid point that's moved more than 5 meters, say. It's just a way to identify which particular objects we want to operate on. This will make a little more sense when we actually look at the template. So again, the boundary condition, so if we have the Earth here, and your model is a small portion of the Earth, if we were to sketch this, sort of a freehand sketch, we have a model here that we're going to mesh, but then we've got the rest of the planet around us. So our boundary conditions can be as simple as a free surface, meaning that there are no boundary conditions. Nothing's prescribed. We can use stress. So if we want to say this is a very large model and there's a tunnel at the base of it, and this is the actual surface, well, we can actually increase the level of stress or define the stress that's acting on the model at the boundary. There are simpler ways if stress is less of an issue, where we might use what's called a roller boundary, in which case you can think of this as a wheel. At this boundary, these grid points are free to move up and down, but they're not free to move left and right. And then in another case, we have what's called a fixed boundary condition, in which case at the base of this particular model, it's not able to move left or right or up and down. And that's just a different way to prescribe how this is going to interact. So for example, if we just had a model, but we didn't have any kind of boundary condition at the bottom, and we turned gravity on, you would see your entire model just fall through space because there's nothing holding it up. Of course, in the real world, in the real mine, in the real tunnel, civil tunnel, there's a whole planet around it. But we've got to prescribe these things first in the numerical model itself. One thing to be aware of with Itasca software is that we don't specify units. So for example, when we look at the template, you will see that there are numbers for properties, but there are no values of units. So the way it works is we use what's called a consistent system of units. And so with metric, for example, we just have to make sure that the units are consistent, meaning that if we start to do math with them, multiply units together, divide units, that when you cancel out all the units, the unit you end up with is the correct one. There are several for metric. There are a couple for imperial, if you prefer to work with imperial units. I think we're a pretty international crowd, so I assume most people will work with metric, but you feel free to work with imperial. That does bring up a couple interesting things. Until I started using Itasca software, I was not aware of slugs and snails in terms of density, but it is a valid imperial unit. And you can see what the equivalent is in metric if you're trying to convert them down here. It's really just a unit of mass in imperial units. The problem set is set up really to work with this system. but feel free to work with some of the others if you prefer to work in megapascals for stress as opposed to pascals. I recommend this one. It's base units. If you're putting in a stress or an elastic modulus or something like that, and it's a gigapascal or a megapascal, it's just as easy to say 10 times 10 to the 6 pascals as it is to say, 10 megapascals. So just keep that in mind. One other point here is that degrees, whenever you're using commands or the data files, they're all going to be in degrees. So we're not going to be using there's no need to use fish, which is one of our scripting languages. In that case, the angles are in radians. But for the most part, you should be working with degrees. Sign conventions. Our software uses mechanical engineering practices. My background is in mining engineering, so I'm used to compression being a positive stress, for example. But in mechanical engineering, where they're really concerned about a lot of tensile failures, tensile failure is positive and compression is negative. So when you're looking at results, just bear that in mind. And kind of a little helpful guide here is that sigma 1 is going to be the most compressive, but sigma max is going to be the greatest magnitude. So that could be the greatest negative value. So just bear that in mind. Okay, so numerical solutions. A model is solved through a series of steps until a steady state solution is achieved. If a steady state solution can't be achieved, then the model is essentially inherently unstable. At each step, the variables defining the state of the model, stress, strain, displacement, strength, etc., are recalculated, and then these propagate throughout the model. Each element, whether it's a zone or a grid point in the mesh, behaves as if it's physically isolated from its neighbor during one calculation time step. So that the time step is calculated really based on the size of the zone and the stiffness of the zone, and that's done automatically. So it's not something you really have to think about, but it's done so in such a way that everything is essentially isolated from each other, and then just gets progressively updated as everything around it also gets progressively updated. So just things move, stresses change, that sort of thing. Typically, a model can be solved within hundreds or thousands of steps, but the larger, the more complex the problem is, the more steps are likely to require. It could be hundreds of thousands or millions of steps for a very complicated model. In the problem set that you'll be looking at, it'll be more on the order of thousands of steps. It runs quite quickly, so you'll be able to sort of iteratively change properties and get a result quite quickly. A model is an exact equilibrium, so it's stable, if all the net nodal force vectors at each zone centroid or grid point node is 0. Practically, though, in numerical modeling, it's very hard to essentially zero out all the noise and reach that state. So what we do is essentially have a convergence level, and a model is considered to be an equilibrium when the maximum unbalanced forces at those points is very small compared to the representative forces in the problem. And what we're going to generally use is a convergence criteria of 1. And so when we look at the template, we'll see that once you've set up a model, and this is all being done for you, so that you have sort of a starting point. But once the model is set up and you've defined the mesh, the boundary conditions, the material properties, the constitutive model, turned on gravity, things like that, then we're going to simply run the model by issuing a command that's model solve. By default, the convergence criterion is 1. In the event that you encounter bad geometry, which could happen because we're running a large strain, which means that those nodes, those grid points can move. So if you have a really weak backfill, it is possible that after some point, um, the the mesh will have moved to such an extent that it will become distorted, and you can get nodes twisting around each other, and then it's just numerically doesn't make sense, physically doesn't make sense, and the model will essentially stop on its own. It'll give you that warning, and you'll know that that is an unstable situation. So you want to make the model material stronger. Okay. So this is sort of a cartoon of a slope, which is similar to what you'll be looking at when you expose the backfill face, although obviously it'll be a 90-degree um, boundary. So when we're running a model, um, we can specify things like a convergence criteria, whether that's 1 or 0.1 or 10. It just it it depends on what um, depending on the model, the materials, how quickly it'll run. So what we like to do is look at a bunch of different things as well while the model's running. So we can look at things like the velocity of the grid points, and we can look at things like plasticity in the model. So what we're looking at here is we have a model where we have very small velocities, 10 to the negative 6. That's probably meters per second, so very small values. The velocity field's very incoherent. So in this case, um, this model isn't doing very much, and essentially it's effectively in equilibrium. But if we have a situation where this slope is going to have some sort of circular slip failure because of the geometry and the material properties, then what we're going to start to see is velocity will become coherent, sort of within the circular slip area. And we'll start to get velocities on the order of millimeters or centimeters or even meters per second, which means it's essentially starting to move. If it's going to fail, then we would expect to see, that's when you would expect to see, meters per second of failure, tens of centimeters. In this case, it's just a few millimeters, so it may just end up stabilizing at this, which would be an indication of a failure mechanism, but not necessarily a failure. And then we can also look to see that within that circular slip region, what the plasticity is. So if we've had yielding in the rock, so instead of being an intact material or at full strength, it is yielded either in shear or tension or compression. And that would give us indication of uh, what the failure mechanism may be in this model. So in a perfect world, what we do is, or in a numerical world, what we can do is we can add history points. So here we have a history at the crest of the slope. We can put in any number of histories, mid-slope, at the base, at the toe, etc., into the inside the model. And we can monitor things like stresses, displacements, velocities, forces, and we can plot those. And so what we have here is essentially the model is running over time, over a number of steps, and we're measuring the x displacement at this point. And so if we use this recommended command, it's sort of a default solve convergence 1. What we're seeing here in this illustration is that we get some initial displacement and then it levels off to sort of a plateau. And that's a good indication that the model is reached equilibrium and it's stable. If, however, we manually guess at a number of steps, so let's say we say, oh, let's just run another 2,000 steps after we've done, say, another excavation or we've changed something in the model. Here we see again, we're getting some displacements in the x direction at that history. But in this case, it hasn't really run to the point where it's really started to plateau. And so that's sort of an indicator that maybe we haven't run the model long enough. Um, And then if we have a situation where, again, maybe we do another excavation in the open pit, we use a smaller convergence criteria. And so essentially what that's going to do is run out the model for much longer. But then on the other hand, while that's definitely reached equilibrium, we've got a nice plateau. Essentially displacement isn't changing with time step. You could argue that you just ran that model for way longer than you needed to, and you could argue that at this point that would have been, say, sufficient. So this is just a little background. The model template is set up for you. By default, it uses a solve convergence of 1, which is basically, in our experience, a good starting point for almost any model. I just wanted to point this out that while we're looking at some histories, and you do have some histories in your model, this sort of information gives you a sense of whether the model is behaving in a stable sense or an unstable sense. And we don't have that indicated here, but in this cartoon up here, if instead of it coming to a plateau, all of a sudden we see that the displacement just jumps, then that is an indication that that model is unstable and not at equilibrium. If you have any questions as I'm going through, just feel free to, let me check if anyone's raised their hand. Nope. Or add a comment in the chat box. I can follow up with that. So part of the problem set, it's really a two-stage problem as I see it. One, you sort of have to change the strength of the backfill until you get a point where it's stable. And then you have to see, in a sense, how stable is it? So the first step is really increasing the cohesive strength of the backfill based on the cement content that you're going to try. Because what we're interested in is how much cement you have to put into the backfill to stabilize it once it's fully exposed and we've mined through. But then after that, because we just don't want it necessarily, we're not limiting it to a stable situation, but we want to have a specific factor of safety, in this case 1.25. So that's where we're going to want to run the automatic factor of safety analysis. I haven't included that in your template, but on this slide, I've included everything that you would need to use to implement that. So once you have achieved a stable model based on some backfill cohesion value, try running a factor of safety analysis. And this is an automatic system. It uses what we call shear strength reduction, where essentially the material properties in the model are systematically reduced until we get a stable solution. Or after, I think it's 50,000 steps or something like that, it can't find a stable solution, so it's deemed unstable. So if you run the factor of safety too soon, you're going to probably run into that situation. But if you find a cohesion that basically lets the model come to a nice stable equilibrium, and then you run the factor of safety, you would expect to get a factor of safety greater than 1. You know, if you put in a lot of cement, it could be 1.5 or 2. If you don't put in very much cement, it could be 1.02. You will notice that when the factor of safety analysis is running, it's kind of using that bracketed approach, and it will try multiple runs before returning to the starting model state. So wherever you invoke the factor of safety analysis, it'll go through a whole bunch of sort of different models as it's reducing the strength of the materials. And then once it gets to a point where it's determined the factor of safety, it'll just return you back to the model state that you started it as. But it will indicate both in the output what the factor of safety is, and we've set it up so that it'll plot it on the model plot. One thing to appreciate that when you're doing a factor of safety analysis, I've put here that the displacements that are reported are fictitious, and that's because, um, say your cohesion's 100, or whatever that means, and then the factor of safety analysis reduces it, and it finds out, it says factor of safety is 1.1, and you see like uh, large displacements, or maybe the factor of safety is less than 1. Those values are fictitious because it's not the actual values that are in the model, but they're the reduced models. Of course, if you reduce the properties, you're going to get larger displacements. So just note that when you're looking at displacements, not to use any that are part of the factor of safety analysis, because those aren't the ones that are associated with the value that you've entered. It's the reduced value that the factor of safety has processed. One thing that's important to note is that the factor of safety analysis must be used in small strain mode only. And so there's a command model large strain off that will deactivate that. You can turn it back on with on. And we'll go through the template, or we can talk about that a little bit more. You can invoke the factor of safety using the command model factor of safety. And then optionally, you can specify a file name, just whatever you want it to be, Fred, Frank, George, bf.fos. It's a string, so it should be in single quotes because it's a text. And the nice thing about that is every time you run the factor of safety analysis, it'll just overwrite that file. And otherwise, it will just give you it'll just use a default name and just add a 1, a 2, a 3 to it, and you'll end up with a whole bunch of save files that you don't necessarily need. Okay. Scripting. So I mentioned earlier, so we do have a built-in programming language called Fish. Python is also available on Flat2D, and you're more than welcome to use these, but it's not required at all to solve this problem. There is again, I mentioned that introductory course that talks about Fish. There are a few references here also about Python and how to use it in Flat2D if that's something you're interested in playing with. But I've just sort of included this slide because I did include what we call essentially fish fragments or inline fish. And they're really just sorry, that should be convenient way of defining variables and assigning values. So we use these square brackets in our data file, and we can define a global variable, in this case, cohesion, and we can assign a value to it. Because we're using consistent units, and in this case, the model was set up really for pascals in terms of strength and stress, then you know by seeing this is that's 0.1 megapascals in this example. What that lets us do, though, is if we issue a command, model property cohesion, so we're defining the cohesion value of some zones, we can just use this as a variable. So instead of having to change it in the command, you can change it up here. And then you can also use it to do math, essentially. So we still have our cohesion defined. We've got a Young's modulus of the fill and a Poisson's ratio. And when we want to assign, for example, say we wanted to assign a bulk modulus, which is just calculated through Young's modulus and Poisson's ratio, we can essentially use equations in these little fish fragments and variables. So it's kind of a compact way of doing calculations. So instead of having to calculate properties or values in Excel, you could just write a relatively simple equation and then add variables to solve them. And then if we just change the Poisson's ratio here or the modulus here, then this value will automatically get updated. But these are provided in the template for a few cases. I think when we look at it, you'll see that it kind of simplifies things. But other than that, there's all sorts of things you can do with fish. There are all sorts of things you can do with Python. You are probably more familiar with Python, and feel free to use it as you need it, but you shouldn't need it for this problem set unless you want to do something, maybe automate something or try to do something more efficient. Okay, 1 second. Sure, there aren't any questions. Okay. So here's the problem set. You should have received a PDF that sort of outlines this, and again, these slides. So what we're asking teams to do is to evaluate the stability of a cemented paste backfilled stope, which is going to be exposed during vertical retreat mining on one side. The adjacent stope is to be mined in a series of blasts. The analysis can be made along a two-dimensional longitudinal section, also essentially plane strain conditions are valid. And we're just assuming that we're looking at the middle of some 3D stope. In the event of instability, we're asking you to make recommendations of an alternative design solution, but not just a solution that's stable, but one that minimizes backfill costs. So meaning we don't want you to put in 30% cement into the backfill, probably be worth more than the ore that we're mining. So essentially, we want to minimize the amount of cement that goes in, but we do want to. We do have some other conditions that we'll see in a minute. The existing cemented stope is three-dimensional. In reality, it measures 72 meters high by 27 meters in length and 15 meters in width. The vertical retreat stope is to be excavated in a series of 6-meter high vertical cuts. And then backfill strengths can be based on 28-day cure times. And we provide some data for you for that. We've built a model template because we do appreciate that there's not a lot of time left in the month and that you're all still probably busy between exams and reports and holidays. So we provided you a template, and you shouldn't really have to do any major modification, but you are free to do so or build your own unique model if you wish. As I mentioned before, the template does not include the factor safety analysis component, so we'll expect you to add that to the template. So here we can see that we've got a series of these 6-meter high stopes, or cuts, I should say, and we're going to take them out one at a time. If we were, this is a relatively large dimension, if we were just to remove everything instantaneously, there would be a sudden redistribution of forces. And in a sense, the model could behave dynamically, and then we would get sort of artificially induced damage. Almost like maybe you guys can relate if you've worked with a testing frame for UCS tests. So those use a very controlled closure rate, depending on the material. You can specify different strain rates, and you might want a different strain rate for granite as for backfill. But if you've ever been to sort of a mining program introductory, like trying to induce students to come into that program, it's not unusual for them to like maximize that and then just basically detonate the core sample. And that's just because the load is artificially in an uncontrolled way being applied to the sample and it explodes. And so that can happen in a numerical model. If you just all of a sudden have a model that's happy, stable, in equilibrium, and then you make a giant opening all at once, then all that material wants to rush in really quickly. You can get all sorts of artificial dynamic effects that will create artificial yielding and numerical instability in the model. And that's just not good practice. It's also more realistic because that might be a different thing if they intended to take out the full height of that stope all at once simultaneously. Then there are different ways we can play with that to do that in sort of a a reasonable controlled way. But this is pretty typical of how they would actually mine it, and so we try to replicate that. Um, and so we excavate a small volume, let that come to equilibrium, do the next one, let it come to equilibrium, next one, next one, next one. If the backfill isn't strong enough, at some point, material may be unstable, and material may start to move out, um, and either in a stable way where it eventually sort of restabilizes, and there's just some displacement of millimeters or centimeters or tens of centimeters. But if you start seeing displacements on the order of meters, remember this is only a 15-meter wide stope. So the displacements of this at this face are in the meters. That's inherently unstable. It's not likely to come to equilibrium, but it may continue to move and move and move further out. Again, because we're running these in large strain, you'd physically see that wall move. On the other side, we have an unmined material, so it's just the rock mass. And when we look here numerically, what we're doing is just defining some of our boundary conditions. So we've got our backfill. There is actually a single column of rock along the right-hand side of the model. And we've included what we call an interface. So essentially, there's an interface with some physical properties between the backfill material, which has one set of properties, and the rock, which has another set of properties. The rock itself is fixed, meaning that this boundary of the rock is not free to move up or down or left and right. However, along this interface, the backfill is free to move up and down. And if you take a look kind of at the top of the model when you first run it, especially if it's a relatively weak strength material, you'll actually see this a gap form, and you'll see it sliding down. You'll see that in terms of displacements and also in terms of displacement vectors. The sliding interface we can assign properties to it. We can assign cohesion to it. We can assign friction, dilation. In this case, I believe it's a 35-degree friction angle, but no cohesive connection. So there's a resistance to sliding friction there. At the base, we have what's called a roller boundary. So it's free to move left or right. So in effect, it's behaving as a frictionless interface, if you will. But it's not free to move up and down. So this is sort of almost like a pedestal that's holding the whole model up. If we remove this and turn gravity on, then the whole model would just disappear out of the plot because it would be falling and accelerating at the speed of gravity, or the acceleration of gravity. On this side here, rather than actually generating material zoning it, what we're going to do is the template essentially defines a series of ranges that are 6 meters high that have names. So like cut 01, cut 02, cut 03. And it's all just boundary conditions. So essentially, this boundary condition, this roller exists initially, and then we're going to free the first 6 meters, run the model till it stabilizes, remove the next 6 meters, run the model until it stabilizes, next 6, and so forth. And at some point, if it's strong enough, the goal is that this entire face will be free. And if it's not strong enough, at some point, you'll likely have displacement of the backfill into this outside of this boundary. We're just leaving the top of the model what we call a free surface, so there are no boundary conditions. So we're assuming things like really that the behavior of the backfill is controlled simply by self-weight. We're not incorporating or thinking about sort of the stress field and the rock around the model. That can have different effects. It could confine the backfill, for example, but we're just assuming that this is self-weighted in this example. So we don't have to worry about how deep the stope is. Okay, we've provided material properties, density, Young's modulus, Poisson's ratio, friction, tensile strength of the material, and cohesive strength. For the backfill, it's to be determined. That's really the goal. And then we would like that equated to a percent of cement content. Um, Interfaces have normal and steer stiffness. They're all predefined, a 35-degree friction angle. And these values are just chosen so that the model runs reasonably fast and that the backfill doesn't start pushing into the rock. If it not enough stiffness there, that can happen. So we provided some 28-day strength results, kind of a mishmash of a few papers. We're assuming this is a paste fill, 28-day strength, 2% cement, zero 0.2 megapascal UCS, up to 12% for 2 MPa. We're assuming that this is a valid relationship. It's not a bad sort of back of the envelope place to start, so we can equate cohesion and friction with respect to UCS. So we know friction, we know what the UCS is, so you can use this equation to figure out what the cohesion is to put into the model. And you may have to iterate between these values. So what we're looking for is essentially the backfill stope must exhibit a factor of safety greater than or equal to 1.25 when it's fully exposed to the VRM slope. So once we've done all those cuts and there's basically nothing holding the backfill back. Also, though, we would like you to minimize the backfill costs. So we don't want you just to go and say, oh, 2% is the biggest number. That's going to be stable. That's the answer, but that's not the economic answer. Okay, so I'm gonna go through the FLAC. A couple of things, we provided some plots for you for contours of displacement, vectors of displacement. The state, what this is telling us is if there's been yielding in the material in terms of shear or tension, whether it's now N or past P. We can see our boundary conditions. So this side is fixed in the x-axis, meaning that it can't move this way. This is fixed in the y-axis, so it is not able to go up and down. And then it's a little hard to see at this scale, but there's an interface here. These are our zones, and of course, our XY coordinates when you're thinking in terms of displacements. We've set up a whole bunch of histories here. It's a little hard to see at the scale, but there's a bunch of different colored dots here that are basically the position of recorders, if you will. And those are associated with grid points. And as those move on the x-axis, we can monitor that. And what we're seeing here is, say for this first position, the first cut that we do, we're essentially getting some initial displacement, plateau. The next cut, we have more displacement, but then it plateaus. Then we're getting less displacement, but what we want to see is sort of this stepwise progression. At this point, we're basically up to the top of the model exposed, but you can see here that if we run this out, we can see that they've all come to a nice sort of plateau. So even though we continue to cycle the model, there's no more displacements along this face. And that's ideally what we want to see. Just quickly, the report, and we will look at the model in a second. So ideally, the report should be less than 8 pages, but there's no formal limit. The layout and the style is up to you. I see you've all picked great team names, so that's great. I guess a reminder, when I was an undergrad, we had sort of a 4th-year report, and we all made up sort of like ABC Mining and different mining company names. Just a reminder not to, and that's all fun, not to refer to yourselves and get carried away to be PNGs or anything like that, unless you happen to be. Um, so that's something that's obviously frowned on, even in the sense of a game. So the submitted report should address the following topics: the problem definition, figure representing the model and the situation. Feel free to do a better sketch than I came up with. Um, Overall approach, including any assumptions, numerical modeling approach, including describing a shear strength reduction method that's involved with factor safety analysis. There's more information in the documentation and our manuals on that. Numerical modeling results, including the design factor safety, what the stable cumulative maximum displacements are. So for whatever cohesion you end up with, that essentially gets you to 1.25 and the least amount of cement, what the displacements are with that set of properties. Stable and unstable zone failure states. So as you're sort of running the model and you're seeing that the situation is unstable, take a look at the plot that shows you what the state of the model is and talk about that. When you're stable, and you have your goal met, what do the failure states of the zones look like there? Which is your final design recommendation? Um, if you can identify any key risks to the proposed solution, and how such risks could be mitigated. So take a look at the overall model, the way we're assigning the properties and the boundary conditions, things like that. Is there something that we might want to think about doing differently, or um, the way that everything is set up, what kind of risks could be involved there, and then how could we mitigate them? So what I'm going to do now is bring up this folder with the template. So everybody should have received a copy of the template. Once you have FLAC 2D9 installed, there's a little icon here, a shortcut to start it up. So I'm just double clicking that. It's starting on my other screen. Okay, so what I'm going to do is just bring that over here. Um, you will actually see a little dialog for helping you to set up your license. It'll ask you if you want to open a previous project or start a new project. Unfortunately, I couldn't move that dialog over to the screen that I'm sharing with you. So what we're going to do is just go to File, and we're going to go Open, and we're going to look for a project file, PRJ, backfill pillar. We're going to load that. And a project is just a combination of all the elements of the model of the project. So it could be data files, it could be plots, it could be save states once you run them and models are saved. So say for each cut, we're going to have a different save state, so we can move around sort of at different states of the model, whether it's 1 cut, 2 cut, 10 cuts, and see on the plots sort of the results. So just really quickly, so we can see, obviously we have file. We can make new data files, new plots. We can open existing files. We can save the project. And then of course we can exit the program. Under tools, we've got all sorts of options. Everything from what the customer title should be. So if you want to put your group name there, please feel free to do so. If you want to change things like the editor, we'll look at it in a second, but if you prefer a dark background to a light background, by default it's light, but a lot of people seem to prefer dark mode. So you can come in here, change that, change the font size, the default font size, how big it is, things like that. If I hold the shift key down, sorry, the control key, and I roll the mouse wheel, I can make that text a little bigger or smaller. The layout of the model is completely up to you. What we can do here is with this little split icon, we can go and split below, we can split right, and so we could have 3 different plots here. We could have 2 different plots and 2 different data files. We can show all sorts of things however you'd like to see it, and we can just get rid of those. Of course, you can resize different elements however you want. If you want to turn off the workspace or this section here called the command console, we can turn that on and off with these buttons here on the left, including the project lists with all the files. The way most Tasca codes work is through commands. Fish or Python if you want to do something really sophisticated, customize, automate things, that sort of stuff. But essentially, it's a series of data files, and we have a data file to clear the memory, start the model, so model new. And what we're doing here, we have a file called master file, and it just calls a series of other programs. And if we look at the first one, sketch, and we look at that, we've got a data file here that basically sketches out our model. So I've gone ahead and pre-sketched the model, and what we can do, if I go over here and I go to make a new sketch, and I just call it something like Fred. So this is where we actually can draw the model. We can go up here, set some default parameters. So I want each zone not to be 10 meters, but 1 meter or 1 unit. I can do that, and then I can simply draw the edges of the model. And you'll see here that we've got these sort of nodes indicating the length of the zones. And then if we just want to keep it as simple as that, that was our model. We can go in here and then we can mesh all polygons, and we get a simple mesh. It's a very simple model, so everything's just little quads. If we had a slope, essentially it works and tries to generate a hex dominant model. So you'll have mostly quad zones, but you may have some 3-sided zones as well. That's all perfectly valid. And then if I was to go here and generate the zones, then we actually have a model in terms of a mesh. Within that, I can go in and pick those zones and then do things like assign a constituent model or set model properties. I guess I have to set a constituent model first. We're using more Coulomb, assign. And you can see down here that every time we're doing something, it's basically giving you some feedback. So it's telling you that model more Coulomb has been assigned to 2400 zones, which are all these zones that are selected. And then we can go here and set properties, and we've got density Youngs, etc. And then we can even do zone distributions and have some distribution of cohesion, for example, with some deviation. Now, as this was happening, if I look here at what we call the state record, everything that I just drew, the sketch, the changing it to a zone length of 1, those have all been recorded in what we call the record. And so what I have done is basically taken this and saved it as a data file. So I didn't actually type all this in, thank goodness. I just drew it interactively and then was able to save it as a data file. And the nice thing about that is then you can reuse the data file without having to redraw it. But you could go in here and change things like if you wanted the default length to be 2 or to be 0.5 meters, then you just change the number there, rerun this data file, and it's done. So you don't have to redraw everything. So I'm going to bring that back to the plot. We were looking at displacements. Now, this is the current state of the model. I haven't saved the model state. So if you are at a point when you draw, if you do resketch it, as soon as you resketch and you generate these zones, it's really important to save that as a save state. And you can just go up to File, save your project, and if there's a new save state or a change in the model state, it'll prompt you to resave. And you can call it whatever you want to call it. And then, just like we're doing up here in the master file, we just call that data file. And you'll have your model instead of the template model. So I'm going to go here and I'm just going to highlight these two commands. So I don't want what I've just drawn because it's not the actual model. So I'm going to clear that out of the memory by invoking the command model new. And then I'm going to call the sketch that was done as part of the template. And rather than using this arrow here to run everything that we see in this data file, I'm just going to go and right click and run the selection. I'm going to discard the model state because I don't want what I just did. And then what we'll see here is what is part of the template. If we look at GP, we can see that this is backfill, this is rock, and that was all done in the sketch mode. I was able to select this material and assign it to the group backfill. I was able to select this material and assign it to a group called rock. Okay, so these two things, this clears the model in the master file. This creates the sketch, so the model that we've seen in the sketches that we've seen in the slideshow. And then if we go to initial, what this does is it invokes large strain. So if there's displacements, we're going to visibly be able to see them. There's some notes. These are just sort of a shortcut command way to do it without having to draw it in the first place, because it is such a simple, essentially two quadrilaterals. So what you're mainly going to be interested in is this variable global COH, cohesion of some value. Right now that's set to be 0.2 megapascals. This command tells us to make the model, both the rock and the backfill, more Coulomb material. We've got all sorts. We can use Hook Brown, there's elastic, there's all sorts of soil models, there's all sorts of sophisticated rock tensile strength models. But more Coulomb is a good place to start. So then we assign properties: density, Young's modulus, Poisson's ratio. The three dots are just indicating that it's a continuation of this command zone property. So we could put all of this on just one line across the entire screen, but this is just a way that we can keep it in sort of a compact form. We're assigning cohesion, and here you can see that we're using this fish fragment to put in the variable. So rather than typing 0.2 E6 here, we can just type it up here. It's a little cleaner. And then everything else should be fixed. And we're assigning these properties to a group called backfill that has been predefined. Likewise, we do that for rock properties. The interfaces are being defined by basically saying, look for these two groups, one called backfill, one called rock, and separate them, the nodes between them along those faces, along these edges here. We're specifying the stiffnesses that we talked about earlier, and initially we're assigning a friction of 0. So we want everything to sort of come to equilibrium numerically, and so we want that to sort of just come down nice and smooth. And later on, we'll turn on the friction again. That's one of the neat things about numerical modeling. We can just change properties, turn things on or off. Here we're defining our boundary conditions. The right side here, we're fixing x velocities in the x direction. So we don't actually fix the position of it in terms of x, y, but if we fix the velocities at 0 and they're 0 to begin with, then they won't be able to move. We're doing the same to the west side of the backfill. and the bottom of the model. And we're not specifying anything at the top because it's free. We're turning on gravity, model gravity 9.81. So again, if you do decide to use imperial units, make sure to update that to be 32 point whatever, if it's feet per second. We're adding a history of the unbalanced forces. And then what we're going to do is solve the model. Model solve elastic. And what that does is first, it automatically increases the strength of all the properties that we've just defined to very high values so that there can be no plasticity, no yielding in the model, which is a really good way to start initially because we're kind of bringing birth to this model and it kind of just all of a sudden the forces are there, everything's there. We wanted to sort of be able to numerically settle down, come to equilibrium elastically. Then we'll turn the plastic properties back on and solve that into equilibrium so that we, again, don't get these dynamic effects and have things yielding artificially. And that's just a kind of a handy command with this keyword elas. It solves it elastically and then it solves it plastically. Then we can save that state, model save, initial equilibrium. And so you'll see a file down here called this. And that's just essentially, before we do anything physical, it's like a good numerical equilibrium. Properties are set. We're then going to turn the interface friction back on to 35 degrees and solve it again. In this case, we're just going to, we don't need to solve it elastically again. It's already in a good state. This command initializes the displacements and the velocities by 0, so it resets them. And that way we don't include in our reports artificial displacements through this sort of numerical stage. We're not really interested in that. We want to see what happens when we start cutting the rock on the west side of the backfill. I showed you that plot with all these different histories here. So this is just a series of commands that say x0 at 6, 12, 18, 24. We're essentially going to record the displacements in the x direction, and they just are assigned a series of different names. Then we're going to save the initial state. And then this command program return actually tells it to go to the previous file that called this file. So that's back to the master file. This master file will then continue on its way. So it will then pop back here onto line 5, go to line 6. It will then call data file cut 01. And this is going to be a 6-meter high blast here at the base. And what we're always doing here is we are freeing the x velocities along a 6-meter height here on a group that's called cut 1. And that was all actually predefined in the sketch. So I went in and basically defined a series of 6-meter edges, and I gave them all names from cut 01 to cut 12, I believe. So rather than specifying a coordinate, which we could also do, we could say, you know, at x0 from y0 to 6, you know, that would be a valid range as well. But groups are just a nice kind of compact way so that we don't have to keep remembering what the actual coordinates are. We just define it once early on in the sketch and it's done. So then we solve that, and that will take a few minutes, depending on your computer. Then we're going to save that state. And then again, we're going to return, which will bring us down to cut 2, cut 3, cut 4, and they're essentially the same. Just sort of, we're restoring the previous state and then continuing to do the cut, solve, save, and then it just goes on like that until cut 12. At cut 12, the only thing that's a little different here is that after solving it, I asked it to step a little bit longer. And that's what gives us that sort of tail that we saw in the slideshow and the plots. And that way, it gives me confidence that we really have reached equilibrium at that stage. So once we're at this point, if you've picked a cohesion that is strong enough that the model is stable, then that's when you want to add another data file or just, um, you know, somewhere between this command and this command, you could type in the commands that you would need to um, essentially go back into small strain mode, because it has to be for factor safety analysis in that mode, and then actually run the factor safety. You'll see that essentially it'll do a whole bunch of automatic modeling, and in the end, you'll see on your, I believe it's the displacement plot, there'll be a factor safety value here. We're not running that analysis, so that value isn't available here for what we've done. But when you do run a factor safety, you'll see a value there, 0.8, 1.2, whatever, 3.7. And again, the goal is to be greater than or equal to 1.25. You can add new plots if you want. So a couple of things. When we're in a plot, there are all sorts of plot items that you can add here. We can add vectors, we can add different zone properties, we can add a scale box, which will put a sort of dimension around the model. If we wanted to look at boundary conditions or plot the interface, that sort of thing, those are all things that we can do. Within each of these plot items, so we've got here zone displacement magnitude. It's a contour, but we can also do labels. So if I go here and I plot a label of density, I don't think we haven't run the initial yet, so density hasn't been assigned yet, so it's 0, but you would be able to see the density, or you could scroll down here and go to properties, and then you could look at a plot of, oh, sorry, because I haven't actually run the model, so there's no constituent model. It doesn't know what properties to plot. But here you'd be able to plot things like cohesion, tensile strength, friction of your material. Or you could even plot the model. And again, it's not assigned yet, but this would plot and show that it's a more Coola model. It's a good way to make sure everything's behaving correctly by getting some feedback to make sure that you've correctly assigned values. So obviously, if you were to try to run the model at this point, you'd have problems because everything's undefined. And this is kind of a way to check to make sure that the properties are available, or that the properties that you think are there, like a density of 2,700, is correct, and you didn't type in 270. You can turn different elements and different plot items on or off with these little circles and dashes. And you can even move these around. You can click and drag on them and they'll move around. And that sort of controls the layering. So the plot item on top is on top. So if something disappears, it may just be because you've plotted something on top of it. To export plots, there's this little icon here. You can click on that and export a bitmap. And that's pretty much what you're going to want to be able to output. We do have PDFs, we do have SVGs. Really, this just gives you a vector of the text. It doesn't give you a proper vector. Unfortunately, right now, everything is pretty much a bitmap base. But that's how you would export that. Yeah, so let's just go back to the master file, and let's run the first few lines of code. And sorry, I appreciate I've gone over time, but we'll wrap up shortly. So I'm gonna not save what I've done here because it's not what I want. So I've discarded. So what we're seeing here is already in just a few seconds, it's run the model to initial equilibrium to that initial state, and it's actually taken the first cutout. So what we can see here, if I was to plot GP fixity, which is really our boundary points, you can see along here we get these red dashes. So it's fixed local X. So it's fixed in the X direction. But if I just, oh, yeah, if you get that, I've locked all these plots so that you can't accidentally drag them around. But there's this little symbol here, lock. If you unlock it, then you're free to zoom in and move it around. So you can see here that for this first 6 meters, those fixities where velocity was set to be 0 have been removed. So this material is free to move. And of course, because of all the weight of the material above it, we're getting displacements here. We can see the maximum displacement is 0.01 meters. So we have some movement, but that's just the first cut. If I highlight this and just run that command, you can see that it's saved that. We go here and we see now we have 12 meters free. So that's how we're representing the excavation or the mining. Of course, if you just run this whole file using this arrow, it'll run everything here and we can just sort of watch it. Here we're looking at displacements of vector displacements. If I go here and I put this back to where we had it, contours, we're seeing contours of magnitude. And you can see here that we're already getting, 1.6, 1.7 meters of displacement, which isn't terribly encouraging because this is 15 meters. So probably the initial template cohesion is not high enough to solve your problem. Also note that this was originally at this height, and so through this process, the backfill is already kind of compacted and displaced that vertical distance, in addition to the displacements that's happening here along the face. What you'll see, I went back to this default console view. We can see that it's cycling. It's basically going to cycle until it reaches a mechanical ratio of 1 times 10 to the negative 5. So as this gets closer to 1 minus 5, then you'll have a sense of when it'll go on to the next step. If we go back to this plot, and again, okay, and notice here, so really this thing is sliding right out. We've got 9, almost 10 meters of displacement. So it's not looking good. At this point, I would probably just stop the model. We've got a little stop button up here. And it'll say that we've interrupted it. I might save this as well, I probably wouldn't bother saving it because it's not the right solution. It's not really useful information. Other than you may want to look at what's happening in terms of the state. So if I go to the state, so you've got all sorts of rich information of what's happening. Quite often, what we're really interested in is what the current state is, not what's happened in the past. So we can click that and we can see that we've got some tensile failure in the zones here, which makes sense. It's kind of ripping apart. And then we've got a lot of shear failure here and here. So, this is the kind of thing that we're interested in the report of what's happening, maybe not at this earliest stage, but as we get a little closer to the actual solution where it's stable. But you can see how it's really just sliding along this interface and then along this boundary roller, and it's kind of just oozing out as we free up this space here. And 10 meters of displacement on something that's 15 meters wide is pretty big. So we wouldn't want to, it's definitely not a stable solution. If we look at the histories, we can see, initially it wasn't doing so bad. It was kind of plateauing. But when we start seeing things like this, it's possible that if we ran a little longer, it would stabilize. But I know in this case that it won't. It'll just keep doing this until essentially the zones become so deformed at some part of the model that it just stops on its own. It says, it's not numerically valid. So that's the sort of thing. Really, the main thing to get out of this is that you're free to resketch the model if you like, but this sketch data set will basically build the model for you. What we want to do is focus here on this cohesion and find a value that makes sense in terms of the percent cement that's being added to the backfill. All right, at that, I'm going to stop. If there are any questions, let me maximize the screen. Please let me know. If you run into any problems, you have my email. Okay.
Yeah, so I have a couple of questions.
Yeah,
Just wondering. So you did mention that there's a hex grid sometimes. Like, is it always quadrangles, or is it sometimes hex, or is it triangles?
no, it can,
Sometimes?
let's see if I go back to my slides. So the nice thing about FLAC 2D is the meshing is automatic. It's relatively easy to model a mesh in 3D, or sorry, 2D. So if we were to look at this diagram, I'm trying to see if there's something, an example here. We aim to have four-sided meshes in our software. It works best that way. I don't actually see one here, but usually what the sketch tool will do is it will create what we call a hex dominant mesh. So it will try to put in as many hexahedral zones as possible. And then if it has to, it will include some three-sided zones. Um, and we generally don't do all TET modeling except in 3DEC. And again, it's all automatic. I think as you'll find that as if we introduce things like circular tunnels or horseshoe sort of curved elements into the model, you're probably more likely to get more tetrahedral type shapes.
Okay. So how much control do you have over the mesh? Like, can you do, say, variable cell sizes if you wanted more detail around a certain area or a certain interface?
Yeah, completely. You'd have to sort of set that up. So for example, say there was a tunnel here, a circular tunnel. What we would probably want to do is when you create the outlines of the model, you'd probably want to put a little box around it. And if we look back even at the sketch tool, um, let's make a new one, new sketch set, blank. So what we have here, let's close that down so we've got a little more room. So there are, I really glanced through this, but we do have in the quick start example that I provided in the links, they have a nice walkthrough with that. But here we've got all sorts of tools for putting in circles, including a quad split, which basically puts a square inside the circle. It just meshes a little nicer. But we also have like tunnel wizards that you have where you can define, more like civil type tunnels. But in the end, this will give you a nice tunnel shape, but you're still going to have to essentially put a bounding box around it. And then sometimes there are little tricks that we need to play by creating different. So if you wanted to have very fine zones around the tunnel, you might put a box around that, specify you want 1 meter zones or half a meter zone length, and then have another box around that that's specified to be twice as big. Generally, when we have a gradation like that, we try to keep it at a 1:2 or 1:3 ratio. So you don't want to necessarily jump from a zone that's 1 meter to zones that are 5 meters. You can kind of work your way up that way. So like go from 1 to 2 to 4 to 8. Um, yeah. So sometimes there's a little pre-planning that goes into it. But if I was to draw a shape around that, and then you can also even come in and move those points, or you can right click and edit their properties and give an exact coordinate. Um, if I select these outer boundaries, I can go up here. And so right now that zone length is 14. Oh, sorry. I could make that, I don't know, 3. And that's going to essentially refine that. And then if I go up here and auto mesh it, you'll see that it's given us something like that. Not my finest artwork, but so quite quickly you can have a mesh at one zone size surrounded by a coarser one, and it kind of figures out the ratio in between. And then you can click on the tunnel, and then over here on the right, we have a group name. So I could call that tunnel. And then I can call that rock. And then when I build the model here, there's the zones from the backfill thing. So I'm just going to delete those. And so I'm left with something like this. Again, these aren't really the boundaries that you would want to have, but we've got some nice tools now in the model pane, which we're in now, where we can essentially automate the boundary conditions. It doesn't actually specify what the conditions are, but it lets us group them. So this would automatically get named to like west, north, east, south, I guess. And then it would try to do the same thing to the internal boundaries. So it might be like west 1, west 2, just depends on sort of the angle there that's involved. But a lot of that can be quite automated, where you can specify it manually. And then when you actually want to assign your boundary conditions, you have a name rather than having to worry about what this coordinate is and that sort of thing. Does that make sense?
Yeah, that was really helpful. Thank you.
Yeah, and if you look at the resource slide with the quick start and go through the quick start, either the tutorial, so there's a video of it, or work through it, you'll get a better feeling for it.
Okay.
I think the one hint I would point out is that if you are doing, if you are working with this, one of the first things I do is I click on this sort of drawing tool and I go to the default edge parameters because everything's really based on edges. And I would specify the length that you want that you're working with, at least to start with. You can change it after the fact, but I kind of find by default it's quite coarse. And so it's fine for a tutorial, but when you're doing an actual model, it's kind of simpler to start out with that at whatever kind of scale you think you're going to be working at. And then but at any time, you can come here and change the zone length or the number of zones on that edge. So we could change that to 1. Now it's going to destroy the mesh that was there, and we probably want to get rid of that one. But if we go here and rezone everything, you can see it's much finer along this edge. And then it's tried to do sort of some kind of ratio as it's moving from this length to this length. And then you can see here it's put in some 3-sided elements. Okay. Are there any other questions?
Yes, one last one for me. Is there a minimum
Please.
backfill volume for arrays of backfill?
Well, in the problem set, we've assumed that you're going to excavate in 6-meter increments. If you want to change that, so what that's going to do is you kind of have a couple options. If you went smaller, then I wouldn't be worried about numerical instability because I know it works for 6 meters. But like if you just took out, what is it, 72 meters? So say you took out half of that, it would be there'd be other things that we would add to the model to sort of ease the model into that. So all of a sudden, it's like all of a sudden if somebody put 2 tons of weight on you, you would just get squished. I guess it probably wouldn't matter if they did it incrementally, but you'd be able to respond better, right? Like, if they put it on 20 pounds at a time, at some point you'd be like, okay, I've got to drop this or move out of the way. So you can respond to it. And the model's kind of like that in the sense that if we just instantly say this tunnel was a kilometer deep, and so we've got really high stresses around here, and then we just took that tunnel out, then all of a sudden, instantaneously, within the first few steps, the boundary of that tunnel would want to push in, and it might do it at a rate that's not realistic. But in fact, it would almost certainly do it at a rate. Depends on the strength of the material. Um, but what you often will see is these sort of artificial um, implosions, and sometimes you want that. Maybe you're studying rock bursts or something like that, and you want to have a high rate of closure. So what we have is a relaxation command that lets us essentially pick a material, some group like tunnel, and then we can essentially gradually over several steps relax it. Um, it's kind of like if you're sort of plotting support versus rock material strength, and you don't necessarily start with the weakest state of the model. I'm not explaining that well. Okay, so have you ever seen like a 2D analysis where in 3D, if you've got a tunnel and you're excavating along a drift or a tunnel, you can kind of put a measurement point in um, at some point and then continue to mine. And if you're monitoring the vertical displacement at that point, what you'll see is sort of this gradual, the tunnel roof will start to close um, further away from the face of the tunnel. And so it's sort of like that. If all of a sudden um, we jump too far ahead and we excavate not 3 meters of rock, but 30 meters of rock, that tunnel's probably not going to respond in a good way. And so numerically, what we do is we play around with things like the modulus of the material, and we can kind of dial that down from being equal to the rock around it to a lower value. And then we're also kind of constantly sucking energy out and controlling how these uh, boundaries are behaving so that it all kind of comes down to a nice convergence in a clean way numerically. And we just delete it and it's high stress. If it's low stress, not really a problem. But if it's high stress, you're going to start to see these artificial numerical effects just because it can't really keep up to it like the Earth. So anyhow, we call that zonking at Itasca, or the command now is referred to as a relaxation or relax command, and it just lets you do that gradually. Yeah. So if you were to take out the whole left-hand boundary condition of that backfill, it might work if it's already like you've got a stable, if it's strong enough, it might work, but I wouldn't really recommend it.
And for the existing backfill design, is there kind of a lower limit on how fine we can make, if you have different zones with different strengths, how big those zones can be?
Yeah, so the sort of the zone size. In the problem set, we've specified 1 meter size zones,
Okay.
but
Yes.
you could play with that. What that will help with is so the bigger the zones, the faster the model will run, but the less accurate it'll be. Smaller the zones, you'll have more zones. It'll take longer to run, but it will become increasingly accurate. But at a certain point, you'll find it plateaus so that the smaller the zones are, you'll get the same answer. But and then that's sort of a good way to sort of calibrate zone size is you start with something big and then you get smaller, smaller, smaller. Um, and then you'll get to a point where the answer won't change. It'll just take longer to get to the same answer. It could help with if you have big displacements and large strain. So like larger zones are gonna start to get twisted and not work sooner. So the finer you make it, the longer you kind of delay that. But if you're getting into that situation in this case, then you're kind of you just don't have a strong enough backfill. And then we don't have it yet in FLAC 2D, but in the previous version of a different product along the same lines, a 2D version called FLAC, we had a tool that would let you do remeshing. So that essentially when it starts to sense these illegal geometries, these weird things happening to the zones, it will actually remesh the zones finer at that point, and then it automatically will transfer all the displacement information to the new zones and the stresses and all that sort of thing. That's something that we will be adding to FLAC 2D, but it didn't make it in this year's release. And where that can be interesting is if you actually want to see a slope fail and see how far it's going to make it. Does it hit the town or does it not hit the town?
Yeah. Cool. Thank you.
Yeah, you're welcome. All right. If there are any other questions, just send me an email. If you're running the model, if something doesn't make sense, I know this is a lot of information quickly. Really the thing to focus on is as it is this line here, line 14. If you adjust this and rerun your model, so you'd change this, then you'd want to make sure to save it. Otherwise it won't get saved. And then you just go back to master file and just run this from beginning to end, because this is really the end state that we're interested in when it's fully exposed. And then keep track of the displacements, the histories, if they're starting to plateau, if they're just running out forever, if we're getting meters of displacement, then that's really an indicator that it's not strong enough, that it's not stable. There is a solution. So at a certain point, you should have a fully stable system. It may not be a factor of safety of 1.25, but then you run the factor of safety analysis. If it comes out at 1.1, then the backfill strength has to go up. And then you know that it will be stable, so you can kind of just jump right into the factor of safety analysis and see what you get. Okay. Great. Well, thank you everybody for hanging in. Sorry that went longer than I had hoped. If you have any questions, you have my email here in the resources. So it's Dave. If you want to, there are links here. So, the FLAC 2D quick start example or getting started with FLAC 2D talks more about the different splits of the screen and the user interface, how to plot things. So that just goes to our Software Academy here. You will have to enroll, but it's free to enroll. And then the full course is, I think, a few $100s, but you should have a coupon code that'll let you take that for free. So this will, I'd recommend trying the getting started with FLAC 2D. It'll kind of talk about the user interface a little bit more detail, and then the overview of the user interface, which will help you see the different components of the model in a little more leisurely time. Feel free, this isn't necessary. It's a 3-day course, so there's a lot of content. But if you wanted to review maybe the factor of safety analysis section, that might be useful. Also, the online help will bring up this web page, and you can see on all sorts of things under FLAC, different tutorials, different examples. And there should be might not be under these examples. There is a factor of safety example. So you can do a search for factor of safety, and then just focus on FLAC, FLAC or FLAC 2D. Okay. Again, if you have any questions, don't hesitate. If something's not making sense, let me know. And we can maybe share any issues with the whole group. even just through a quick video or a quick email. Okay, and I think everybody knows the timelines and the prizes and all that. I didn't really include any of that. Good. Well, thank you for your attention. Again, let me know if there are any questions or any issues arise. And other than that, good luck with it. I hope you have fun playing with FLAC 2D. I think that's the right way to think of it, is an opportunity to play. And we'll go from there.
Well, thank you.
All right.
Yeah.
Thank you. Good night or
Thank-
good morning, as the case may be.
Yeah, Junior is not here. I guess he has to go to the office. So
Okay. Yeah. And so I will save the video, and then I'll give you guys a link if you want to just share it with everybody, and then they can focus on what they want to focus and fast forward through what they don't want to.
Yeah, we can do that. That's good.
Excellent.
Yeah.
All right. Well, thanks for all your efforts, guys.
Yeah, thank you, David.
Yeah. Take care. Bye-bye.